All right, so how does SCR catalyst work? So it's a SCR catalyst, it's a NOx catalyst, so it reduces NOx. Typical uses are in the exhaust of, normally not in the exhaust of a car, in the exhaust of big engines to meet emissions limits and that sort of stuff. So how does it work? It's pretty neat. It works through chemistry, but it's not very difficult chemistry. So let's walk through it. So the whole goal is to turn NO, which is an emission. It's regulated, and if you pollute too much of it, you'll get in trouble. So you turn it into N2 and H, it's not H, H2O. Well, how do you get the H? Where do you get that from? Well, you get it from injecting something into the exhaust that has H, and typically you inject ammonia. Ammonia is NH3. Okay, so you got your NO, you inject NH3, and it goes through the catalyst. Let's just draw a box for now. It goes through a catalyst, and it ends up as N2 plus H2O. Cool. How? Okay, first of all, you have to overcome the activation energy. Ooh, so you have, what do you have? You have NO, and you have NH3 on the left, and on the right, you have N2 and H2O. We don't know yet whether this is above that or if that's below that. We don't know yet, but we'll do the math and we'll prove that it is. The most obvious thing is no catalyst has a high activation energy, but with a catalyst is a low activation energy. So how does that work? And that to me is the most interesting part. So a catalyst, this specific catalyst, is made up of very polar molecules, or very polar atoms, I think. I think it's atoms, not molecules. Specifically, they use titanium and vanadium, mostly. These are polar, and what I mean by that is, like, if you choose oxygen, it's -2, because this is, what is it? Noble, I think. This F would be a -1, oxygen is a -2, -3, -4, and like this is a 0 and this is a +1. And the interesting thing is with all the metals, I drew too far-ish maybe, I don't know exactly, but with all the metals, they can be different. So they don't, like, this isn't a +2, +3, +4. It's not like that. They can be more, because you're going to end up with like +5, +6, +7, +8, and this is noble, and then you're going to get a +9, +10, +11, +12, +13, +14, +15, +16, and that means that's a noble, which means this is a +1, and that's not the case because this one is noble. So the metals can be not anything, but they can be very polar if you combine them with the right stuff. So the idea is a catalyst is made up of either titanium or vanadium bonded with usually oxygen, I think. So it looks like a lattice or something. So you have like one, let me just draw, you know what, I have dots. Oh, I was gonna say I have these dots, but they're like super small, so I'm gonna make my own dot, 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 dot. Let's do a couple more. So let's say that these are, say that's vanadium. Let's make it easy on ourselves. Let's say it's like that. Cool. So you have the vanadiums there, and you have the oxygens here, and they're all interlinked. Cool. So you got your molecule that's super huge, and that's what the catalyst is made of. So how does this work? Well, now let's draw the chemical equation. So I kind of drew it up here. So I will stick to it. Move this over a little bit. So you have NO plus NH3, N2, H2O. Do I have enough things? Okay, let's assume there's, what did I assume? You have to actually do math. 6, I think it's 4, 6 and 5, 6 and 5. Does that make sense? That's 10 N's. No. Dang it. What is it? Fine, I'll do the math. You can skip forward if you want, but I'm doing the math. And let's say this is 1. B. What would this be? Should be 5/3 equals 2B. That is 5/6 equals B. Okay. So we got A is 2/3. B is 5/6. C is 1. Cool. Okay, so this is our balanced equation. Now we use enthalpy of formations. Woo. NO. Maybe I should have gotten these numbers ahead of time. Actually, I think I have them. Do I? Yes, I do. And I'm just going to trust them. So I have 1 times positive 90 for NO, and I have 2/3 times NH3, which is negative 46, and that goes to 5/6 of N2 is 0, plus 1 times H2O, which is negative 241. All right, I don't even have to like finish the math. The negative 241 just wins it out. So the right side is at a lower energy state, so it's preferable. So that means it looks like this. So left side is above the right side, and that means when you get up to here, and it can choose whether to go back to where it started or go down to the right, it'll choose to go down to the right because it's a bigger drop and it likes being at low energy states. Okay, so the right side's favorable. So the right side is favorable, but there is an activation energy because the left side is not 0. The activation energy is 90 minus 2/3 of 46, which is 30, which equals 60. So it is not 0. Which means there is activation energy that it has to overcome, which sucks. But catalysts lower that activation energy. So how do they do that? So the way it works is you send your NO and NH3 through the catalyst, and what happens inside, erase this. So you have your, doesn't matter what I draw, you have your NO. And since the vanadiums are super polar, let's say they're -4. So they're like extremely polar, right? Doesn't really matter what it is, they're like -3 or -4 or something like that, depending on how many oxygens there are, and oxygens are -2, so they're kind of polar. So these would probably be, they would be plus something. They could be +4, they could be +3, or I don't know. But you get the idea. Vanadiums are super polar, so they literally pull on that molecule. They literally pull it on all 4 sides, and they rip it apart, because what's actually going on here? So NO, so you have N, I think it's double bonded to O, is it? Well, yeah, technically, but it's like, it'd be like a N-1 or something. NH3 is better. You have N, and you have 3 H's. So it'll help actually if I draw that in here. I know I have like infinite freaking screen I could draw on, and I'm choosing to draw super small, but I am choosing it, so you have to deal with it. So you have that, and the vanadiums, which are super polar, they literally pull the H's off. They pull it apart. So because like by default, the H's are attracted to the N because N is -3 and H is +1, so they're opposite, and they attract towards each other. So they freaking pull towards each other. But now that a bigger force, vanadium over here, it's freaking pulling on that hydrogen harder than the nitrogen is pulling on the hydrogen. So it ends up pulling it away and rips it apart. That's literally it. So now they're ripped apart in here. Now you have all the molecules. So in here, in the middle of the catalyst, you're up there. And then it can pick which side it wants to go on, and it'll pick this lower side. And let's say the catalyst is like long, like that long. It'll stay separated in its individual like atoms until it gets to the end. And then at the end, it'll pick which side it falls on. At the end, it'll fall down. But yeah, no, that's literally it. And then it falls down to the side it wants, which is a more favorable side, because the right side is a bigger negative number. So it'll go to N2 and H2O. That is literally it. So NOx or SCR catalyst, it literally just pulls. It's made up of superpolar molecules like vanadium or titanium, and they literally pull on the molecule inside of it harder than it's pulling towards itself, and it rips it apart. So that is literally how it works. That is how it effectively lowers activation energy. That is it.